Excellent. Okay. As I was saying before, I think we're going to have a lot more time to check in with students starting next week. My goal is to go ahead and I have a big deadline at the end of this month, which is upon us. So I want to be able to dedicate a lot more time into like checking in with all of you and making sure that everyone has completed the to-do list and to get you your document for what's going to be the midterm. I kind of give you a prelude to understand what it's going to be, but I actually have to draft that document up and share it. And so I'll pack it into the repo once I've authored it, and then I'll make an announcement on Discord as well. So you can go ahead and look out for that. And so if you want to stay in the same group that you might have already been in based off of doing your to-do list, you can go ahead and do that. If you want to like find a different group, or if you weren't in a group before, now you want to find one, use the Discord to try to find group members, right? So just make an announcement on the general, inside the general chat area in the channel, and you should be able to do that. Okay. With that said, I kind of want to finish off at least the concept of numerical representations of integral values over the course of this class. And I think the last thing we have besides, so we already talked a lot about encoding integral values with a number of considerations, right? Not just the number of bits that you're going to use to encode your value, which is going to impact your range, but also what set of integers are you going to use, whether you're going to use just the non-negative ones or if you're going to use negative and positive ones, which is also going to impact the range from 0 to some positive value to having it shift towards a set of negative values and a set of positive values. And of course, that requires two different encoding schemes. So depending on whether it's unsigned or signed, is going to matter what the interpretation of that is. And we saw that you don't necessarily want to just cast from one type to the other, because if it's a negative number, it's going to turn into just a really big number between sign, or if it's a really big number, it could turn into a negative number. So again, just a small pitfall you should be aware of when working with C, because really what it cares about is what the binary sequences are and the context for any given type. So once you stick to it, once you declare a type, typically you want to try to stick to it. It's the safest approach. Okay, so we've talked about how we represent numbers, and at the end of the day, we find a creative way to take whatever it is we want to represent and express that in the form of numerical data, right? Whether it's image data, whether it's text data, or whether it's musical or audio data. So the next thing we need to do, now that we have our numbers represented, how can we go ahead, I guess let me switch over to there, and actually start doing our arithmetic processing. So like when you start learning Java, you learn Python or C, right? We have all the simple arithmetic operators mapped to a set of symbols, like the plus symbol, the minus symbol, the division symbol, the asterisk symbol, the multiplicative symbol, right? So how can we manipulate the bits in our binary sequences that's consistent with the arithmetic that we perform? And so think about the arithmetic operations we care about. We care about addition, we care about subtraction, we care about multiplication, and we care about division. And what are some of the implications about some of these operators? That's what we're going to kind of take a look at today. I don't think this will take the entire time. And the next part, after we talk about integer arithmetic, we'll start talking about fractional numbers and fractional representation. So that's where we have approximate values that can have decimal points or very large numbers as well. And my goal is to talk about that next week. So let's see here. Let's go into so let's start with unsigned addition. So with unsigned addition, one thing we need to be wary about is how it can affect the max limit size of our binary sequence. So when we're mapping a set of values, that's kind of arbitrary. We're like, oh yeah, we'll use 8 bits. And this is the number of different values I can map to 8 bits. Once we start talking about doing operations, now when we're doing unsigned operations, right, we can never have a negative value. We can only ever go down to 0. But it's possible that we can take a legal, let's say 8-bit value, add it to another 8-bit value, and actually result in a value that has to be larger than 8 bits, right? Does that make sense? intuitively, right? Okay, here's a challenge for the class. What if I express my binary sequences in the form of 2 to the power of W, where W is the width of my binary string, right? And so if I have a 2 to the W string and a 2 to the W string, and I add those together, what is the biggest new binary string that can be produced from that? Let's talk about, so we're talking about bounds. What's the maximum bound that if I wanted to encode that overflow, if I wanted to capture the actual addition of two, let's say 8-bit values, how many bits would it take to guarantee I get that result? I'll give you a moment to think about that. Yeah, and you add those together. So does everyone kind of see the concept? So as a proof of concept, try to do this by hand. Let's do 4 bits instead of 8 bits to keep the math smaller. What's the biggest value you can have for using 4 bits? Let's just talk about the binary representation. What's a binary representation that represents the maximal value that can have? 1, 1, 1, 1, right? All the ones are toggled on. They all contribute towards the sum. Okay, so that's a legal value for a 4-bit number, right? So what if we add that with another max value? What's the other max value you can have? Well, it doesn't have to be unique, right? So it too can be 1, 1, 1, 1. So why don't you do that? If you have pen and paper, or if you can mentally do this math, take the binary sum. Has everyone done binary addition before? Okay, do the binary sum of 1, 1, 1, 1, 4 ones plus 1, 1, 1, 1, and tell me what size binary string that is. 32. 32, and how many bits? 8 bits. Oh, wait, 32. So it was 1, 1, 1, 1, right? And then 1, 1, 1, 1. 1, 1, 1, 0, 0, 0. Okay, so let's see here. And let me see here. Let me see if I can't do this here as well. New window for the class. Let me see if I can do 1, 1, 1, 1 plus. So it's just going to be, and I'm trying to remember, can I do this? I'm trying to remember, does anyone remember the Python? Remember how to translate that easily, but let's see here. So let me think. This is 16. This is my 16th place. This is going to be my 8th place. Well, so let's see. Give me the sequence really quick. Okay, so here we have, let's see, our 1's place, our 2's place, our 4's place, our 8 is right here, and our 16 is right there. So it ends up being 30, right? So we have 15 plus 15, right? And so the next bit over then, so if we have the ability to encode up to 16. So let's do this. So we got 1, 1, 1, 1, right? And so if that's the equivalent of saying 15 plus 15, then that means here is our 16 spot, right? That means that this here is our 32 spot, right? Now we're not at 32, right? So we're at the 16 spot, right? And let's see, 14 after that, so 8, you know. And then here, let's see. Let's see, we don't have long to. So we increased our bits then by 1 then, right? We start with 4 bits and now we have 5 bits. Okay, just as a proof of concept, try with 2 5-bit values at max and see what you get as a result from that. And see if you can't find a pattern here. So this is the sequence here. So we stated that, actually, let me see if I can do this. So 1111 plus 1111 is equal to, yeah, perfect. Okay, good. So this is an expression where we can actually see it. So if you see this, if our max size of bits is 4, and so when we talk about addition, we're going to talk about addition requires that our bit strings are aligned, right? So there's the possibility that they're misaligned. What do you do? Is it possible? So first of all, if you have misaligned length of your binary strings, let's say a 3-bit string and a 6-bit string, you couldn't actually add those together, right? Because they're different lengths, right? You need the same number of elements to do a vector operation like that, right? So, but there's a way to do that. How would you normally do that? Yeah, right. Yeah, you can zero fill, or if it's two's complement, you can 1 fill depending on like your encoding. But you can expand your binary sequence by just taking whatever the smaller amount is and giving it more bits, because the bigger binary sequence can encode the same value as the smaller one. But notice what you're doing, whether you realize it or not, you are effectively casting by size mentally for you to be able to do that operation, right? Now, but so what we're going to harden a constraint. We're making sure everyone understands this constraint. One of the constraints about any arithmetic operation is that since we're working in vector spaces, it has the same number of elements as the left operand and the right operand. Okay, once we agree upon that, now we can start creating hardened rules. We can understand what the maximal growth rate with addition might be. And so this instance, no matter how many bits you add into your addition, it's only ever maximally going to produce a string that is 1 bit more. And it doesn't matter. So like we were playing around with 4-bit strings, but that's true for 32-bit strings or 128-bit strings or 1,000-bit string, right? If you take the maximal amount of both those, add them together, it can only ever produce a binary string that has 1 additional bit to carry the carry over. I think I even have a code example of this. Let's take a look at it. Let's see here. Let's clear this. What do I have here? No, ls. Okay, let's take a look at this. Overflow. Oh, we didn't talk about overflows. I guess we are talking about overflows, yes. Yeah, this is exactly what we're talking about. Okay. Okay, it's GCC 01 overflow with bits for 1200. And let's call this overflow for our application. And actually, let's take a look at the code as well. Okay, so quick idea of what we're going to look at really quick Not going to spend too much time. I'm going to include my limits header. I'm going to include my standard input output header. We're just going to have a main function. Inside this function, what we're going to do is I'm going to use limits to access the max value so that I don't have to memorize what it is. So here we're going to get our unsigned integer max value, and then we're going to see, okay, what happens when we add 1 to it? And this should cause a wraparound, right? So with computers, so we see when we're allowed to increase by additional bits, right, we would get the actual value. But in a programming language like C, we're not allowed to arbitrarily expand the bit sequence, so we're constrained by it. So for instance, if we are in a character encoding, it's limited to 8 bits. If for some reason I do addition that produces a 9-bit sequence, what's going to happen is it's going to discard the most significant bit, probably trigger a carry flag in the system, so the system knows that a carry occurred, but the actual sequence then that gets updated is going to be whatever is inside the 8 bits that it does have, starting from the least significant bit going all the way up until it runs out of bits to encode. Okay, so what we're going to do is we're going to look at the maximal value, and in this instance, we're just going to add 1, just 1 right over the max, and for unsigned values. And then we want to look at overflows for signed values as well. Now, overflows for signed values can go in 2 directions, right? I could either add on a value that's too high, or I can subtract from a value that's too low. So I can have a negative wraparound or a positive wraparound. And so this is a very simple code where all I'm doing is assigning to either really big or really negative, really positive or really negative values. And then I'm just going to give it a little push in one way or the other. Let's take a look at that. So here, I'm actually going to print out the actual value of my maximum unsigned int. And it should be of no surprise to you, since I don't have negative values in unsigned values, that it's going to be twice the size as the maximum signed did, right? Okay, so we're going to take a look at that. Then we're going to add 1 to that. And so we just roll over back to 0. Because what would have happened is if we had an additional bit of information, that's the thing that then gets pushed over into that overflow space, but doesn't exist. So essentially, we're kind of doing the equivalent of a modulus operation inside of our binary space, right? We fill it up, and then we carry everything except for the most significant bits. Okay, let's take a look at this as well. So you can see in our signed overflow, it's doing the same thing, right? Only now, instead of rolling over to 0, we're going to roll over in such a way that our very high positive number, by adding 1, becomes a very big negative number. Which the interesting thing about this now is if I did a relational operator between those two, right? Like this value plus 1 is greater than just that value, it would tell me false. That's not greater than, right? Because it's going to translate it as a negative value. So notice how this can have like pitfall, like hard to detect errors if you don't realize you've actually added 2 numbers that produces an overflow effect, right? Because you can look at it and mentally you're like, yeah, that number based off of the value of A and B, when I add them together, it should be bigger than this number. But to the system, if you overflow the address of the encodable space for that value, the range, it wraps around. So it's something to be aware of. It's not going to happen often, but this is a pitfall that would be difficult to try to identify in a code base. Same thing with this minimum value, right? I have this really small minimal value. If I add 1, now all of a sudden it becomes my max value. I'm sure y'all pretty much looked at this already, though, in assembly, right? Yeah. Okay. Okay, so now the book, the one thing that I do appreciate about the book is that the book does have some really nice visualizations on it. And so I don't know why the TVs aren't coming on. So let's take and look at the visualization that it has for this idea of overflow, just so that you can see how our binary sequences are mapping inside of our domain. So with the book, it's using 4-bit spaces. So with 4-bit values right here, which is what this sub indice is. This sub value of 4 is representing a vector of 4 bits. Okay, so with 4-bit representations, if I was to plot this across a 3-dimensional plot, with the idea being this. My 3-dimensional plot on one dimension can be what is my current value of u, which is one of my 4-bit numbers. On the other, so let's say this is my x-axis. And then let's say on this other axis, let's say this is my y-axis. My other 4-bit number can have another value. Now I can sum those together. And when I sum those together, it can produce a new value that has to exist in that same spatial domain. Now, this particular instance, you see how this uses the word with inflation? This means that it's allowing me to increase my spatial domain to accommodate a summation that doesn't exist between u and v. So this is the easiest of the kind of 3-dimensional visualizations they give you in the book so that you can understand what you're looking at. So this is our sum function that takes your u at any potential value, takes your v. And so the 3-dimensional, the height is based off of what the combination of those two aggregate to, what they sum together with. And it doesn't limit the value. So it's okay, whatever binary sequences you need, it can then resolve to be up to 32, which makes sense, right? Well, almost 32. 32 is here. It's 30, right? Because it's 15 and 15. So it's gonna be. Notice we have these are in 2 unit increments. So 32 is at the very highest, and if we go to the very highest, which is 15 here and 15 here, this is our highest peak. That's at 30. That line right there. Okay, so everyone understands what this visualization represents then, right? This is the behavior of summing 2 4-bit numbers, probably the most complicated visualization for one of the most easiest concepts to grasp. Okay, let's show you, though, how this has to be modified if we constrain sum to have to encode into the same spatial space that u and v exist in. And so it's going to create a different propagation of our wave. You can actually see the point at where overflow will then occur at. And so here we have the same image, but notice we have our 14, or 15, our 15, and now we're going to limit the sum to be no greater than 15 as well. So when we get to where we get any combination of values for u and v, that would sum up to 15, effectively the behavior becomes a modulus operation, just rolls over. So this is just a graphical illustration of where our normal behavior then lies for sum when bounded based off of space on encoding, and then where our outlier, where our overflow behavior would occur, where we start having to truncate those most significant bits, which means that when we reinterpret those as a 4-bit sequence, it's going to start rolling over again because we've run out of unique values. So we start reusing the values we've already used, and since they've already been defined, we go back. And of course, the obvious thing here for detecting an overflow, if you needed to do this, was you can do checks, right? One check for detecting one of these positive overflows, for instance, with unsigned addition, is if your summation between x and y produces something that isn't greater than X itself. Because with unsigned values, you can't have a negative, right? That means those are two positive values. Even if one of them is 0, you should at least have the same value X was. If at any time you were left with something smaller, then you know an overflow has occurred. So if you have to check for overflows, the understanding how these rules work lets you know how to detect for an overflow inside of your code, or how code does that, like how the system is able to evaluate for that. I don't want to pretend like this is something you're ever going to actually have to do, but what you should know is this is what the system needs to do to know what's happening with our numerical values when we start using them for processing. So again, it's one thing to use computer systems to store information, right? That's great. But we want to do more than storing information. We want to produce operations on it. We want to be able to process it. That means transforming our data from its initial state to some new desired state. But we have to ensure that as we transform it, it's in a state that is legal and it's what we expect it to be. And so these are the rules that we abide by inside the system that ensures that something as well, I say as basic, I mean, arithmetic, you learn it from an early age, but it's a very sophisticated set of concepts that have developed over a period of several thousands of years, right? And has been the reason why society and civilization has been able to hit where we're at today. And of course, we already showed that with signed arithmetic, we have to check for overflows for both ends. And that means that you can do a check at either end. And so here we can just see when we can detect for positive overflow, we would do that the same way that we would do for unsigned values, where we can check if the summation between two values becomes less than. And then we can also do the inverse of that for a negative overflow, when the subtraction of two values produces something that's a greater magnitude than what we would expect. And so we can define those almost into cases, right? Where you have a negative overflow case, your normal negative outcome, your normal positive, and your positive overflow. Okay, let's see here. Let's take a look at another example. Let's quit out of this. Let's see. I think I have another one where we're actually going to look at the bits in overflow. So here we have a function that we'll just call add binary. It's going to take a binary string in the form of a character pointer. It's going to take another binary string in the form of a character pointer. It's going to take another binary string, which is going to be our result, and a size of our binary string. So actually, let's say before we read the logic inside of this function, let's jump into the main function just to see how it's used. That way it motivates what the implementation is. So jumping down to the main function, we have two binary strings, 1111, 1111. So this is effectively the example I gave to you earlier. I'm going to give you the size, 4 bits. I'm going to go ahead and produce a result, which now we know based off of bounds, because of the rules of addition, will never be more than what the initial set of binary strings are plus 1 bit. Now notice I'm doing plus 2. The plus 2 is because I also need the null character because it's a string. Okay, then I'm going to do an add binary here. So now that we know this is adding 2 binary strings together, we're going to do a for loop that does this for us. Inside of our for loop, we're going to iterate over starting at the most significant bit. And until we finally hit the index of 0, we'll decrement, because we're going to parse from left to right, because that's how we process strings. Okay, so then once we do that, we will go ahead and index in to go ahead and convert our characters to integer values. We'll actually just go ahead and sum those together with whatever carry flag we had. We'll produce a sum. we'll go ahead and do the modulus on on binary to determine whether it's going to be a what the value is there. We're going to go ahead and impute that into our result, and then determine if we have a carrier or not. So essentially, this is a modulus divisor. It's like the same as integer division, where we're deciding how we're going to decide when to add a unit and then carry a unit because we have two lines. Okay. Not super interested in the logic of that, though, because we're trying to motivate a different concept. So let's just run this. What is this? This is 0, 1. And this is output. And let's call this bits. And let's just take a look at what the outcome is here. And so here you can see this is probably what we already stated before. If I have 1111 plus 1111, I get my new 5-bit result from it. So what we've already done by hand. But now you can see a piece of software that does the same thing. What is the next out of here? Then the next one is going to be my 2's negation. Perfect. Okay, and so I just want to kind of contrast our 3-dimensional plot of sum for signed numbers versus unsigned numbers. So with signed numbers now, remember, you have a negative overflow, you have a positive overflow. Again, what you're probably thinking of is these numbers kind of linked almost like a doubly linked list together, right? Where you can go in either direction. That's a good conceptual model to have. In terms of creating this 3D-dimensional model, you can see this right here, the middle would represent my normal space of sign between two additions, and my overflows are represented here and here. So again, you can see this visual mapping where you're like, well, most of the time with a function, you want it to map to a unique value. But since here we've eclipsed the space, you can see a set of U and V values produce the same outcome, sometimes 3 times, which is less than ideal. Okay, let's talk about 2's complement negation. So 2's complement negation is when we want to be able to flip the sign bit of our binary string, right? So if we want to turn a -3 into a +3, there's what? There's 2 binary operations you can do. Do you remember what those are? So this is what the system will do. The system does this for 2's complement. So again, it's important numerical representation. If we're going to build from these very low-level theoretical concepts, how do you turn a -3 into a +3? Like, is it simply you flip the bits? That's one of the first things you do, right? You take your bit sequence, you flip it. And so one of the beautiful things about having your leading 1 value as the sign bit means that if that gets flipped, now it's a positive sign. Now it's negative sign. But that's not enough. What's the other thing you have to do for your 2's complement negation? Because there's not a one-to-one correspondence, right? There's, like, for instance, on the instance of 1 byte, a signed byte, what's my most negative value? -128, right? What is my most positive value? It's +127. There's an off by 1 there. Off by 1 because we group 0 as part of the non-negative terms, because 0 is part of the unsigned set of values. We always start counting at 0 in computer science, to the point of when we do our split for encoding, the zeros for the positive side, which means it'll always be 1 value less than the number of negative values. So if we want to have a clean, discernible way to take a binary string and very quickly and easily flip it, then we not only have to flip the bits, but then we have to add 1 to it as well. And did you cover that in assembly as well? The idea about how you can translate your values between positive and negative expressions? Perfect. And I think I just have a very basic application we can look at just to motivate that. That's my 0, 2, my 2's negation. here, which I don't want to spend too much time. At this point, I think the logic to get it to work in a piece of software is going to take too much time to walk through than it's worth. So let me just run it. I'll show you. Be free to read the logic. You should now know the syntax well enough to be able to parse this. But what I care more about is to actually just illustrate how this code will translate into us being able to flip a binary set of values so that we can parse it as either positive or negative. So you understand what the system's doing when it's not displayed inside of a piece of software. Let's call these twos neg. There we go. Okay. And so here, to give you an instance of this, we can have the original binary string. And so in this, the one reason why this code is a little lengthy is I want to show you as much as possible. So I not only want to show you the binary sequence, but I want to show you also how we parse that binary sequence to translate into an integer, assigned integer value. So in this instance, this is our original binary string, which represents -5. So if we do 2's complement, which we're going to flip the bits and add 1, we will then parse that as +5. So quick and easy way to be able to transform between our, which is the entire point of 2's complement. And this table right here just highlights some unfortunate results that could potentially happen when we go ahead and perform operations that enforce us to be within inside a certain encoding space. So here with 4 bits, the least value, the most negative value is going to be -8, right? And it'd be +7. So you can just see some operations of what we would get as we start performing the 2's complement and then the increment on it, right? So it's 2 operations. The first is to flip the bits, and the second is to increment by a single bit. And it shows you how we go from 5 to -5, from 7 to -7, from -4 to 4, to 0 to 0, and from -8 to -8. Perfect. Okay, done. We're done with addition. Oh, subtraction is effectively addition, right? Can we all agree with that? So let's move on to multiplication. Okay, I'm going to ask you this question, and if there's a max bound on addition where we only have to add a single bit given 2 bit vectors of a constrained size, is there a well-defined max bound given 2 bit vectors when we do multiplication? Is it as cut and dry with the multiplicative property as it is with the additive property? What do you think? No. Multiplication is so much more complex, right? So the concept of multiplication is a complex one, right? Because you're taking something, and if you think about multiplication as being able to do successive repeated amounts of summing based off of the right operand. So suppose one way of thinking about multiplication is giving a right operand. We will sum it against itself a number of times to the right operand, right? Very primitive and crude way, but you can see how that produces something that's very, very, very large potentially, right? And it gets larger and larger the more that your left operand can be. I mean, does that explanation make sense? So if the idea behind summing was we were simply, I guess the intuition I'm trying to impress upon you there about one of the concepts that drives the multiplicative property is that with summation, we only ever add 2 bit sequences of like the same size together once. But if you think of multiplication as being able to self-sum something X number of times, that's like adding that bit sequence to that bit sequence to that bit sequence to that bit sequence to that bit sequence some arbitrary number of times. It can grow tremendously. So multiplication is a lot more difficult to try to capture that behavior, right? So I don't think they even try to do 3D like representations of that. But let's kind of dig into how multiplication is done. That's the more important thing here is how do we do multiplication? Did y'all already do multiplication division with the integers in assembly? Oh, I won't spend too much time on this then. So you already know how long multiplication works and the concept of how you would do this by hand, right? Which is not too different than how you do this with decimal numbers. You just do it with binary numbers. And so you keep offsetting the number of spaces. So say, for instance, I had decimal 11 and decimal 6. I represent decimal 11 as this top operand. And then with long multiplication, I'll then represent my decimal 6 as this bottom operand. Well, one way to actually process this is I can go ahead and I would do the same way I would perform the multiplication by offsetting based off where the digits are at. So this is 110, right? So at the least significant bit, well, that's all going to zero out, like 0 times these 4 bits. So each of these instances in the long multiplication, it's going to be 4 bits for each row I create. So I'm going to do the multiplication based off of just the zeros place. I'm going to do the multiplication based off this ones place or these twos place. Let me use that term, twos place. And then I'm going to do this multiplication based off of these fours place. So since this is 0, I'm just going to zero out those 4 bits. And then I offset into being now in this twos position where my least significant bit is. And I'm going to then do my 4-bit computation there. So this is a 1, so I just repeat it. And now the last digit is going to the one in the 4's place is a 1. So I'm going to repeat that. Then I'm going to go ahead and I'm going to add those together. And that's going to give me the size of my string. Or it's going to give me the new string. But notice I have to pivot by a bit for each unit that's inside of my rightmost operand or my bottommost operand, right, in order to do the summation. Okay, so this is pretty much how you probably learned how to do this by hand, right? Okay, so I want to map that into how we can resolve that to be nothing more than shifts and additions. Did you learn how to do that effectively in assembly too? How to represent that? And did you do this just by hand math, or did you also program these concepts? So if you programmatically wanted to do multiplication, which conceptually is a very costly thing. Imagine if you tried to do this by doing a for loop, and well, I mean, kind of that's what we're doing here in a way. So I have a better slide for this, but one way we can do this, let me go to the other slide. And I actually have code here we can show off too. Let me see, where'd that other slide go? Well, when I get to the other slide, we'll talk about it. But you can see effectively what's happening here is one way of representing this value is we're going to take our binary string, which is our topmost operand, the leftmost operand, which is my 11, my 1011, and we're going to shift it. We're going to shift by 2 spaces, which is happening here, right? And then we're going to add that by shifting by just 1. You see how this maps into what's happening here? And then I'm not going to do this one because that's all zeros. I could, but it doesn't contribute anything. So does everyone see how this process is effectively using a set of operators that are available to us that's doing the same thing we would do by hand here? You see how we're shifting this? We're shifting this topmost operand, this 11, by 2 spaces. And the reason why we're doing that is because we have this unit here that we have to multiply it by. And we're shifting this one here by just 1 space, right, to the left. So if I shift my original value by 2, that represents this unit here, and add it, because that's what we're doing here, right? We're doing this addition here. Add that to a shift by 1, and then we don't have to add anything here because that's where we were zeroed out. The sum of that is going to produce Well, these two binary strings, which when combined, because it's just shifting that by 2 and it's shifting that by 1, I add those together, I'm going to get the same binary string I get here, which is going to give me a 66 in integer values. That's how multiplication is done. Our multiplication in bitwise operation is just shifts and pluses. So that's what makes it so efficient. That's what makes it so fast. And of course, because your number can grow so large, we truncate, right? And the thing that always gets truncated is the most significant bits. So the thing you're always left over with is whatever the least significant bits that fit into that encodable space is. Let's take a look at some of this code. Drop that. Vim 03, boop. Okay, binary multiplication. Don't care. I mean, I'm going to give all this source code to you. It's well commented. I want to just run it so you can see the results. I'm not going to spend too much time explaining it. But if you want to know how this code works in C to produce these results, you'll have it in the repo. Okay, let's see. GCC, what is this? 03 now. And let's call this bin mult. Perfect. And there we go. So suppose we want to multiply these numbers. Notice these are different numbers now. I didn't use 6, I used 5 this time. Then you can see, based off of the shifts that get performed, this is the shift based off of shifting from the 0 position, plus shifting from the 4's position. And notice the 2's position, where there's just 1 0 that's been pushed to the left, isn't there because this was zeroed out, right? So then that's going to give me the binary sequence that just goes ahead and sums these together. And then this gives me, is that the integer value? I can't really see that part of my screen. Does it give me the actual integer value as well? Perfect. So actually, the reason why I like to have the source code, though, is unlike a slide, I can change these values up. Let me see, where did I put these values again? Here they are. So first I have to enter into my insert mode. And so here, so let's say instead of 101, I wanted to make this 110 like the slide. Okay, and so here, let me escape out. This as well. Okay, let me escape out. Hey, give me my escape. Okay. Let me move this thing. Okay, quit. Okay, now let's go ahead and run that. And so now notice I have my numbers updated so that we could see we no longer have 1011. It's now going to be 10110 because the place at the zeros is a 0, so it's not going to contribute towards the sum. Then in our 2's place, we're going to shift that by 1 and then add that to a shift in the 4's place. Anyway, you can play around with that, make as many binary digits as you want and see how it results. I think the concept is pretty evident, though, of how that works. So there. Okay, so now let me show you truncation, because that's the more interesting thing. Let's clear this. And again, for the purposes so that you can actually see the source code, I'll give it to you here while I start to compile it. Look at it at your own accord, really. All I'm doing here, though, is I'm creating 2 numbers. I'm going to multiply them. I'm going to show you what happens when we try to truncate, what the actual value should be versus the value it's going to report as. And let's call this trunc. Okay, and let's run our trunc. So here, you could see the truncated value. So you can see the full value between these very large numbers is going to eclipse what can fit inside of an integer value, an unsigned integer value of 32 bits. So if I do the full result in 64 bits, you can see this is what I should expect. But look at what I end up getting here. And clearly that's not the right answer, right? Like clearly when you have a value that's all zeros in both of them, how am I getting the term 80, right? So you can look at it, not even know what the actual number is, and like, that's not right. But it kind of is right in the fact that if I had those missing bits, it would parse to be the appropriate thing, but it rolled over. But this is just an example of also what to expect. Now, obviously, truncation and overflow, this is another form of overflow, right? These overflows are much more likely to happen with multiplicative properties than with additive properties. And again, it's something that's good to be aware of because I want to highlight that I did this simply by multiplying two numbers together, right? So you can easily do this in your own code. If you're finding erroneous behavior, if you want to know why C has a bad reputation, it's for reasons like this, right? Like there's lots of ways that you can fall into pit holes that then you spend hours and hours trying to figure out why. And it's not something obvious. It's not like it's a limitation in the way that like your sequence of bits are being encoded and you've overflown those. Okay. Oh, I have some topics here. Let me go here. Okay, let me see what the current questions are. Chat. Oh, we've had lots of communication. How many bits to represent the value of the sum? Oh, yeah, that was the question. Sorry. I think you can. Oh, thank you. Someone showed me what I can do inside Python to get the binary sequence. And then shift in the bits left. And yep, very good. Extra 0. A lot of good comments is what I see on here. We didn't hand do these in assembly, but I did years ago, and it's not fun. Yes, yeah. Binary math by hand is not fun at all. And sometimes they'll do that just to train you, I think. So you have expectations. But fortunately, most of this stuff you don't have to do by hand or even touch, depending on what domain you go into. It's just good for you to know these things because this is how everything operates at a very low level system. And so it's like, it's true. The jobs you're probably going to get are going to be using frameworks and using high level languages. And usually like what your job is kind of going to be like for many people, not everyone. There's lots of roles out there for software engineers, but I would say probably a decent number of jobs is equivalent of plumbing code, right? You take like one pipeline of code, you take another pipeline of another framework, and you create a widget that merges them together. So you're playing around with a lot of, not even on top of high-level languages, but frameworks built on top of high-level languages that are already designed to do tasks. Then you have to learn how to use the framework to do a specific task. Even if that's what you end up going into, having this low-level appreciation of what the system is doing will aid you to catch small bugs or know how nefarious agents might try to compromise your system, especially when we get into things like the bomb lab or the attack lab, where you can kind of see where you can try to give the system something that you know won't process to try to run unsigned code. Like, again, once you have the understanding that everything inside your system is just sequence of bytes with context, and you can somehow put the sequence of bytes you want and give it that context to the system, suddenly you can run an application you're not supposed to run. Okay, and so here we have our 2's complement of our multiplication. So here we're just showing you the value of X. We're showing you the value of Y. We're showing you what the actual multiplicative properties should be, but also what the truncated value is, right? And of course, what the truncated value is if I take the least significant bits for whatever my sequence is. Notice I'm using 3-bit sequences for my X and my Y. So if we're actually using a constrained spatial domain of 3 bits, everything that produces from that operation should only be 3 bits. Anything that overflows outside the 3 bits gets lost. So yeah, we get some of these wonderful results like 3 times 3 produces 1. Okay, yeah, and here, this is the example I was showing before, where we kind of have, if we wanted to have like a pseudocode example of how we can do that, we can take our sum as 0, and then for each index in our bit vector, we'd see, okay, if that bit vector at that index is 1, then we would sum based off of taking that x, whatever our x value is, and shifting it by that number of index values. Okay. And of course, we can't end our discussion of how we can go ahead and process on our integral number sets without also speaking of division. So we talked about how essentially subtraction is the same thing as addition. And so multiplication has a related property to multiplication, but it's not exact, right? Because when you start having things, what's one of the issues with having things? It has to, it might not be evenly divisible, right? And so that's an important concept. So with multiplicative properties, you can always double something, right? That never causes any issues, but you can never always have something. And so here, let's go through the process. So these are just some examples of how we can perform some logical shifts. So the concept is effectively the same though, right? When we divide, we're going to shift by powers of 2 towards the right. So with multiplicative properties, we were shifting to the left. So the concept's going to be the same, but the big thing we need to do is know what are going to be the rules on how we handle things that are not evenly divisible. Like, do we round down? And so this is an instance of a table where that's what we decide to do. There's other instances where, okay, we could do our 2's complement division. So here, incorrect rounding arises when our simple performing right shifts on negative numbers with 2's complement occurs. So if we want to try to, on the instances of on negative numbers, we don't want to round down, we want to round up, right? To supplement for that. And so this is just a table to illustrate based off of the state of the number, whether you're going to do a round up or round down to be able to get a better approximation of what your division should be. Division naturally is a very lossy operation, though. It's much different than the multiplicative properties or the subtraction or addition, right? Inherently so. Like there's so many more, like, how can I express this? Division is the reason why we realized we needed decimal places, right? It's why we have a modulus operator. It's the reason why we have an entirely different number set, right? Division was the operation that broke things down. Like you had ancient mathematicians as like, yeah, we have every expressible number that's countable, 1, 2, 3, 4, and we can express any ratio by just taking an integer and dividing it by, taking an integer and dividing it by another integer, right? But no, you can't, right? Like some things only exist as that operation. Like 1 over 2 resolves to be 1 over 2. So that's, but we have a number set now, or we have not a number set, but we have a mechanism to express that using radix points, right? So fractional numbers, 1.5. But those are naturally lossy, right? They can produce things that aren't really the divisional quality of your 2 integers that you're dividing against. It's just, division is a very interesting thing. Another interesting thing along the same line, small sidebar, is exponential powers, right? You can always exponentially grow something, but the inverse to root something is where we actually start getting our complex numbers from. It's the reason why complex numbers are the square root of -1. It always defines as such. It's because once you introduce exponential numbers, like, oh, there's all these other numbers we can't even represent. We don't even try to represent it except using a multiplicative property where we multiply by I, which represents the square root of -1. Because that's the representation of that number that just does not exist. It's a hole in our number theory. So we represent that number as an operand that can't resolve to anything besides that. It doesn't reduce any smaller than that. So it's become a constant in and of itself. So yeah, the evolution of numbers can be quite a kind of interesting. But going back towards our dividing, you could say the expression that we use for correct rounding would be effectively this. And it all depends on whether our most significant bit is 1 or 0. If it's a signed value, is going to determine how we're going to shift. We're going to shift it by, we're going to do our right shift. So what we're going to do is we're going to do our right shifts so we can get the most significant value. And based off that, then we do left shifts back. I'll show you a code. I don't have a code example for this. We'll take a code example of this next class. But that will finish us up on our integer arithmetic, which I'm thinking was just something that you've already covered, right? So this is all probably repeat material. So, well, how far did y'all go into rate exponent values? Because that's the last thing we need on chapter 2. And I don't think rate exponent values are used in the data lab at all. So rate exponent values are super valuable to know because there's, again, 2 number sets that you really use inside of your numerical representations. Either the integer data set, which we just spent like the last 2 lectures discussing. That's our countable numbers. That's our discrete numbers. But you also have fractional numbers, right? And so that might be necessary for representing when the concept of continuity is important, where you have an infinitesimal difference between one unit and another, right? And it can be however big or small you need it to be, right? You can customize the amount of space between units. That's the fantastic thing about fractional numbers, right? So whereas in countable numbers, the unit of space between my 1 and 2 and 3 and 4 and 5 and 6 is set. It's constant. It's not true with fractional numbers, and that's why it's so useful. It allows me to create a weighting on the distance between 2 values at any given time. Sometimes when you're modeling a concept, that's very important. To be able to have a smaller distance between 2 units than another unit. And because it's the rate exponent value is designed where we can keep adding any set of values to the right of the point, we can keep making that space smaller and smaller and smaller and smaller, infinitesimally smaller. Okay, so wait, let me ask the question again. How many did y'all cover that? The concept of how you model the floating point values in binary sequences? Or did you only stop at integer values? Okay, so we'll actually do a full lecture of that next week. So something for you to actually whet your appetite on and say, okay, I know how to do integers numbers 2 times over. Now we're going to see how to do floating point numbers, which have some really interesting consequences. And you're going to really see why you don't ever want to trust floating point numbers. Now, I see I still have about 6 minutes left. Do I want to use my 6 minutes to kind of just cover the data lab? I don't think that's enough time to cover data lab. So probably what I'll do is I'll go ahead and just conclude today's lecture right now. But what I will say is data lab is online and available. Probably what we'll do next class is actually just have a quick introduction into data lab. And I might even just have you all break into groups and spend the class hour working on your data lab together where you can potentially ask questions and whatnot. So I think that's what we'll probably do for Monday. And then on Wednesday, I'll pick up and do a lecture on floating point numbers, and then we'll be done with chapter 2. I'll also try to get you the actual rubric and the actual assignment sheet for the presentations we'll be doing.